If you go back just a few decades, these devices were a common sight on industrial buildings, warehouses, agricultural structures, and residential rooftops across the United States and Australia. Today, walk through any new housing development in the country and you will struggle to find a single one. They are called turbine ventilators or whirlybirds. And independent testing has proven they can reduce peak attic temperatures by as much as 37 degrees Fahrenheit and cut cooling costs by nearly 15% without consuming a single watt of electricity or relying on any electronics whatsoever. But if they worked so well, why did we abandon them? And if the test data is as strong as it appears, should we be bringing them back? Let us find out. And honestly, this is one of those technologies where the more you look into it, the stranger it gets. Millions of people today are spending thousands of dollars trying to solve a problem that older buildings often handled with nothing but airflow and physics. Moving air through a building without burning fuel or drawing power is one of the oldest engineering solutions mankind ever developed. We have covered the method Persian architects used to accomplish this multiple times on this channel, tall masonry windcatchers called badgers. They were built to channel desert breezes down into the lower levels of a building while drawing hot, stale air out through the top. But they were far from alone. During the Tang Dynasty, Buddhist monks incorporated natural ventilation channels throughout underground cave complexes to regulate temperature and air quality. And by the Middle Ages in Europe, air was considered one of the 4 fundamental elements, and the way a building breathed was treated with the same seriousness as the breathing of the people living inside it. All of these were passive systems, relying on the geometry of the structure and the prevailing wind to do the work. The push towards something more mechanical began during the Industrial Revolution. Deep mines needed a way to keep workers alive underground, and engineers responded with fire-driven ventilation systems and hand-powered wooden fans. By the 18th century, the Houses of Parliament in London had installed a primitive mechanical device called a blowing wheel to flush foul air and replace it with fresh. And by the 19th century, engineers like David Boswell Reed were constructing steam-powered ventilation systems for hospitals and barracks, where airborne disease made the movement of air a matter of survival. But every one of those systems demanded fuel, infrastructure, and ongoing maintenance. The real breakthrough came in 1910, when an engineer named Samuel Ewart patented a spinning cowl designed to sit atop a roof and actively draw air out of the space beneath it. Ewart's original patent describes the device as a solution for both ventilation and the prevention of chimney downdrafts, the gusts that would force smoke back into a home. Unlike everything that had come before it, his device required no fuel, no electricity, and no human involvement of any kind. Ewart's design was simple, yet remarkably clever, combining 3 separate physical principles that work together to solve a problem every house quietly suffers from. During a typical American summer, solar radiation heats the roof surface and turns the attic into a thermal reservoir. Temperatures inside that space can exceed 150 degrees Fahrenheit. That heat does not simply sit there. It radiates downward through the ceiling and into the living space below, forcing the air conditioning system to run longer, work harder, and consume more electricity just to hold the same temperature. According to the U.S. Department of Energy, every degree of attic temperature increase can raise your cooling load by up to 4%. In many homes, the ductwork carrying cooled air runs directly through that superheated attic, so the air is warming back up before it even arrives in the rooms it is meant to serve. The entire purpose of attic ventilation is to interrupt that cycle. Move the hot air out before it has a chance to radiate downward. That is precisely what Ewart's turbine was designed to do, using 3 distinct principles working together. The first is Bernoulli's principle. As wind passes across the curved vanes of the turbine head, the air is forced to accelerate. When air speeds up, its pressure drops. This creates a zone of low pressure inside the turbine that generates a suction effect, actively pulling warm air upward from the attic and expelling it outside. The critical distinction here is that unlike a static vent that simply sits there and waits for air to drift out on its own, the turbine ventilator uses the kinetic energy of passing wind to physically drag air out of the building. The stronger the wind, the harder the turbine pulls. But here is what most people do not realize. The turbine keeps working even when the wind stops. It also draws on what is known as the stack effect, the natural tendency of warm air to rise. Because warm air is less dense than cool air, a building fitted with soffit vents at the eaves and a turbine at the ridge develops a gentle pressure gradient that pushes warm air upward and out through the turbine, even when the vanes are completely still. The third principle is the venturi effect. As air is compressed through the narrow gaps between the spinning vanes, its velocity increases, further lowering the pressure inside the turbine housing and accelerating the exhaust cycle. All three effects reinforce one another. The result is a device that sustains continuous negative pressure at the highest point of the building, pulling hot, humid, stale air out and drawing cooler replacement air in through the soffits below. And this straightforward design has proven to be genuinely effective. A study by the Air Infiltration and Ventilation Center found that installing a turbine ventilator increased attic ventilation rates by an average of 15% across a full year, with improvements reaching up to 50% when wind approached the unit from its optimal direction. Data gathered in the San Diego area showed that a properly installed turbine system reduced peak attic temperatures by as much as 37 degrees Fahrenheit, translating to an average reduction in energy bills of 14.6%. To put that in concrete terms, a standard 12-inch turbine moves between 250 and 350 cubic feet of air per minute at just 5 miles per hour of wind. A 14-inch unit pushes that figure to between 350 and 500 cubic feet per minute. And because the device consumes no electricity, every dollar of cooling savings is a pure net gain. But those numbers come with a significant caveat, and it is part of the reason turbine ventilators have been disappearing from rooftops across the United States and beyond. A study from Deakin University found that while a single 12-inch turbine could achieve a flow rate of roughly 150 cubic feet per minute, the resulting air velocity inside the roof space was only about 1/3 of a foot per second. In ventilation terms, that qualifies as still air. Their conclusion was that a single turbine is frequently insufficient for the thermal demands of a modern home. And this is where correct sizing becomes essential. Most building codes call for 1 square foot of ventilation for every 300 square feet of attic floor space. But in hot, humid climates like Florida or Texas, many professionals recommend doubling that ratio entirely. Performance limitations are only part of the story, however. The more damaging problem was mechanical failure. The spinning head that defines the turbine is also its principal point of vulnerability. Over time, the ball bearings degrade from moisture, dust, or inadequate lubrication, producing a squeaking or grinding noise that travels through the roof structure and into the living space below. Cheaply built units are especially susceptible, and over the years, this gave the turbine ventilator a reputation for being noisy and unreliable. And this is probably where opinions split. Some people swear these things are one of the smartest, low-cost cooling systems ever put on a roof, while others think they are outdated relics that should have stayed in the past. There is also a subtler engineering problem known as short-circuiting. This occurs when a turbine and a ridge vent are both installed on the same roof above a shared attic. Because the turbine pulls air more aggressively, the ridge vent can reverse its function and begin drawing outside air inward, pulling rain and snow with it, rather than exhausting warm air out. For this reason, most roofing professionals advise choosing a single exhaust system and committing to it. And since ridge vents are simpler to install, the turbine is typically the one that gets left behind. Beyond the engineering, there is also the question of appearance. Turbine ventilators are plainly visible from the street, and in the American housing market, curb appeal directly influences value. Ridge vents, by contrast, are shingle-over installations that are nearly invisible from ground level. Homeowners associations across the country have regularly restricted or outright banned turbine ventilators because they interrupt the clean, uniform roof lines of modern suburban neighborhoods. And even in Florida, where state law protects energy-saving devices, many associations have worked around this by requiring turbines to be placed only on the rear slope of the roof, which may not align with the prevailing wind direction and reduces effectiveness accordingly. Building codes have added another layer of difficulty. As American homes have grown tighter and more energy efficient, codes like the International Energy Conservation Code and California's Title 24 have begun requiring mechanical ventilation systems capable of guaranteeing precise air exchange rates. Because a passive turbine's performance depends on wind speed and ambient temperature, variables that cannot be controlled, it falls into a regulatory gray area that is increasingly difficult to navigate. So the genuine question is whether turbine ventilation is something we should all be using. And the honest answer depends entirely on where you live and what you are trying to achieve. In hot, windy climates, the Gulf Coast, the American Southwest, or across much of the Sun Belt, a turbine ventilator remains one of the most cost-effective tools available for reducing your cooling load. A single 12-inch unit runs between $20 and $100 in materials. A professional installation adds between $100 and $300 per unit, depending on roof pitch and complexity. For a standard 1,500 square foot attic, 2 units are generally adequate, and in a southern climate, the energy savings can recover the installation cost within 3 to 5 years. Because proper attic ventilation prevents shingles from overheating and the roof deck from trapping moisture, the device can also add years to the life of your roof. But in cold climates, or in homes with modern high-performance building envelopes, a turbine is likely not the right fit. In winter, interior moisture can freeze the vanes solid, shutting the system down precisely when consistent performance matters most. In an airtight home, where mechanical ventilation is already managing air exchange, introducing a passive exhaust point can disturb the pressure balance the system was engineered to maintain. For most homeowners, particularly those building new or re-roofing, a ridge vent is probably the more practical path. A full-length ridge vent spanning a standard roof delivers over 900 square inches of net free ventilation area, roughly double what 3 14-inch turbines would provide. Because that ventilation is distributed evenly along the entire ridge rather than concentrated at 2 or 3 isolated points, it eliminates the dead zones that turbines can create in the corners of an attic. There are no moving parts, no bearings to wear out, no noise complaints, and no letters from the homeowners association. It sits there, quietly doing its job year after year. If you enjoyed this video and want to keep learning how to become more self-sufficient and energy independent, subscribing and sharing is the simplest way to make sure this kind of knowledge keeps being found.